Okay, my outstanding friends, I'm going to get right into it. Do you think it would be important to understand if there was giants, which they talked about in the ancient biblical and ancient texts of all the cultures, not just the Bible, the Quran, all of them had the same story about dragons and giants. Well, this is a giant fingertip. It's been DNA tested. And I will show you, I broke this piece off so I could get down inside to get the blood. This is the fingernail. That's the fingernail. That whole thing right there, that's the fingernail. This little pad right there is the bumper that goes between bones so that you rock on there instead of crunching your bones. Vein and artery. That is a fingertip. Now, not only is the fingertip there, the fingernail, the fingerprints are still on it. 3 feet long, and here's the fingerprints. Now, I told you how to break that piece off, and you do, because you can't get any blood out of it. It's like a rubber bag around here. That's what they call grip skin, and that's this. And all I did was whack it with a big, I think it was a 5-pound sledge, bam, and it popped just exactly like that. That's just a slab of skin. And there's the sweat pores and the fingerprint ridges. Now and it's also been DNA tested because I went down inside and got blood. In fingers, they're saturated with blood. I mean literally saturated with blood. So I went down inside and got the blood out of it. And I had it DNA tested, and then I had other ones here. This one right here is a lung. This is actually the lung right here itself. That's the size, just like it is in us. Not too much bigger or smaller. And it's flat as a pancake on the back. Because all of this stuff happened at the same time on the Great Flood. And this was the paper I wrote and submitted it to Yale in 2015, along with all my evidence, DNA, CAT scans, and all that rest of that stuff. Now, let's take a look at that stuff. All right, so I showed you I sent DNA off from this giant fingertip, and I sent it off from this lung here, and I also sent it off from this hand, this is 3 feet long. This is just a fingertip. Now, I had this down as 3 feet wide, but I think it might be wider than that, but it's wide, and it's a human hand. It came back human DNA. Now, take your left hand and splay it just backwards like this. What do you see? You see this pad coming around here, this pad right here, you see it? You see the cleave right here? That's this. That's this cleave right there. This is a tendon that you will have running down your hand as well, attached to this bumper pad. And you can see there's a bone or something attached back here. I don't know what was attached there, but something was. And these are human. This was tested as mitochondrial DNA human. I'll show you the DNA test in a minute. Now, this silvery stuff is that grip skin, which, like, I smacked the other one and it just broke right off. The same thing, they're just peeling off. It's very, very, very tough. It's highly keratinized. That means it's intended to be able to wear off and just be replaced. It's like a rubber glove on your hand. It really is. Now, your thumb goes off to this side. Your little finger goes off to that side. Tendon goes through the middle. The cleave is here. That's nothing but bumpy stuff. And there's another bone would have attached right here. They just come apart. And it happened because of the Great Flood. And I have the fingertips, and I had the CAT scan on the fingertips. I have knuckles. I have a knuckle with the bones in them and everything. Even still has the muscle wrapped around the bone. Okay, so I showed you this hand here, and like I say, I think it's between 3 and 4 feet wide. This goes back 15 years probably almost. And I did take parts and bits of it, and I studied it for a long time, and then finally nobody would pay attention, so I had the DNA test done and the CAT scans. And these are the CAT scans I'll show you in a minute, but this is the fingertip from one of these here, from that hand. Now, that's the pad, just like on the bottom of your hand, has a pad just like that, little bumpers and all that. Right at the end, this is what they call the apical tuft. You see the little fibers coming out of it, that round thing? And that is what locks in all your little tendon things. This is where there's a tendon tab, locks right in there, and it comes down your finger so that you can pull your finger back and forth like this with that tendon. All right, now this, you don't see much in this. Now I broke this piece off to get down to where the bone is, because this round piece right here is the bone. Let's look at it in the CAT scan, you'll be able to see. But don't forget, you can't see really anything in there. You can't see that there was a fingernail. You can't see where the tendons were or the blood supplies or any of that. But now once you see it in the 2D, the 3D is not as good as the 2D. 2D is the surface, all kinds of ways they do it. Jesse Gromont and Associates did 7 CAT scans for us. Absolutely phenomenal, phenomenal work. Best people you could ever do business with. Fabulous. And this was this fingertip. All right, what do we see? First of all, that's the bone. And I'm going to tell you right now, that is a thumb. And you say, oh, Roger, how could you tell it's a thumb? Well, because the bone is offset. Take your own thumb and pull that in. You see this side is flat and that side lumps over. That's the way it is with thumbs. They have a lump, and all the rest of your fingers don't. They're right straight down the center. This was a thumb. I can't remember what it was, left or right, but you'll be able to figure it out. Now, that right there is a tendon. That's a tendon, big heavy-duty tendon. That right there, that little black spot, is the blood supply. All right, so here's your tendon with the stalk in the center. There's your blood supply running up with it. There's your bone. And on this side, your other tendon. And there's the blood supply there. One of them's black and one of them's white. And that's exactly what happens with the colors of blood. They're two different molecules. It's FeO2 and FeO2O3 and FeO2O2. The 3 oxygens is the artery blood. The 2 oxygens is the vein blood. Now, one or the other, I don't know which one is which, but it's obvious one's different than the other. Now, I broke this piece off right here to see if I could find any bone, because you can't see it in a CAT scan. Let me show you the CAT scan, and then I'll show you what I did to the bone. Here's a CAT scan. This was the piece that I broke off right here. And it was attached right to the bone. So I can see the bone now. All right? But you can see there is still some differentiation between the bone and the meat. But not much, not much. And the only reason it's there is because there's a heavy-duty membrane that surrounds the bone. And not heavy duty, but now also you see here, you see this surface like whitish looking color. That's different because it's skin. It's the skin is just a taste different, but it's so transitioned that you'd never see this unless you had a really, really trained eye. I'm fairly well, seasoned at doing this. Now, so what I showed you was here is this thumb. Now, right there is the bone. You see this? The bone comes around here. Right here, I can see actually there is still some little tiny bits of bone left in there. And they usually transition almost 100% completely. And I have another bone here. You see this bone? That's the cartilage. Everything stays perfect. Now, this is completely transitioned too, except that one little white spot. You see that white spot right there? That's bone. It could be tendon, but I think it could be tendon, but it's one or the other, which did not transition into basically mud. This is a mudstone, they would call this. And all it means is it was invaded by mud that was surrounding it, and eventually it all became the same molecular formula. It's because it's nucleophilic invasion and substitution is the process that allows invading molecules which surround the damn thing to work their way in and replace the existing molecules. You got entering group and leaving group. Look it up, nucleophilic substitution. And that's what happens here. That's what all my stuff is. Except some of them didn't substitute, really. They just, like this here. This just looks almost like it was when it was brand new. Hold on. And then the beauty about this stuff is it rehydrates almost instantly. You put a little bit of water on it, and it gets nice and red. Look at that. I just put that on just a second ago. It's highly hydrated, and it's because of the silicates, and there's a whole bunch of little chemistry things going on. But some of them, like this, just didn't change at all, basically. It just got hard. And other ones turned from a bone to a stone to just mud. But it was what it was. And they say that Yale agrees with all this now. So this is not something that shouldn't be understood. But the scary thing for them is the giant sizes. But my three things here I showed you, this one, the giant hand, and a huge, huge fingertip, 3 feet long. That equates to a person about 160 to 180 feet tall. Now, you want to see the DNA reports? Of course you do. All right, these are the 3 samples that I had done. Now, this is what was done. DNA extraction, PCR DNA sequencing, and analysis to determine what kind of a creature it was. Now, when it says DNA extraction, that means the samples that I sent them, which I extracted the samples from my specimens, drilling deep into them, not surface squabbing or any of that business. I opened them up basically a little. All you need to do is get a pin drill to go about 1/8 of an inch below the surface, and then go down and you take the blood right out. And there is just blood all over these things. And I'm not kidding you. And some of them run out wet blood. As a matter of fact, hold on, did I show you this? All right, this is the lung that I sent. Well, I didn't send the lung. I sent the sample off. And look at this. Look, it's saturated with blood over here. I drilled a little hole down into and took some of the blood out. That's all you have to do. Just a pin drill. Look at this one. This is another lung here. You see, you can even see the alveoli. You see it? All of those little holes are the sacs that are in your lung, which is these here. All of those holes. And then in those sacs, the air goes, and the sacs are coated with blood. And some of the blood was still left in here. And when it came out of the mud, the blood came too. And I have other ones. I have a ton of blood. Comes out of a lot of them. Now this is what upset Yale and caused them not to be interested, because they were giant humans, and it changes basically everything they've been saying about geology and the whole 9 yards. And I know they understand this, because they even changed the name from geology over at Yale to earth sciences or something, or planetary sciences or something like that, because also Mars has the same stuff. Mars is identical to here, identical. The stuff that's laying all over Mars and that's what I did. I contacted NASA about this. And then NASA funded Yale. And Yale just basically rewrote my paper. And I had already given them all that stuff. And here's my buddy Caesar. Here's Caesar the goose. I call him Caesar Augustus. Now, there's his little nose job or whatever they have in their nose. There's his feathers, the pattern of his feathers on his head. You see that? Isn't that cool? These things, it's exceptional preservation. Yes, there's no question about that. Now, here's his neck. Normally you won't see much because it's just transitioned into basalt. That's the artery. Now let's take a look. And you'll actually be able to see more if you start thinking. All right. I couldn't help myself. Now, This right here is an artery, and this is the back of Caesar's head. All right, this is all the collagens and kerogens that protect and coat. Now, look carefully. You see around here? And then you see the black. Whenever you see the real blackish looking stuff, that's where it's meaty and bloody in this particular one. Inside here, that was probably where the bones were. And this would have been his tongue or something like that, this other color. Everything's about colors and patterns. You see the roundness of his throat? This is the center core of his throat, it looks like to me. And whatever, this is his throat, or bones or whatever around here. And then he's got, bones on the outside. So he's got neck bones, he's got bones on the outside, he's got an artery here. And probably the tongue was right. Well, I know the tongue had to come out of there this way, and I'm sure this is it. So take your time. Just look at that. All right, you see it? See the different colors? You see the different coating on the outside of the edge there? Where it turns brown and goes to black? That's where the feathers were. Right there, that little dot in the center, that's his throat. And right here, this appears to be something, and this appears to be the other side of the something. They always have a opposite to this. But if you look at it, you can see that's something to do with his, I don't know what, his neck vertebra, and that one, the same thing. And here is his neck right in the center. All three of them in a row. Bip, bip, bip. And if you look at it, you can see this pretty obvious. But you have to stop and pay attention. They say, oh, that's just a rock. No, it's not. If you know how to pay attention to things, you can understand them. But to pay attention it just doesn't happen anymore. Now let's look at his tongue, because I don't think we can see anything there. I can see it's a different pattern and a different color. That's what I go for. Patterns and colors. Because tissues all have different colors, depending upon what type of tissue it is. And in certain cases, the tissue colors can be so unbelievable. It's incredible. Like this opal heart. Where do you see this? All right, I'm going to leave it with this. But when I said that things can get very, very colorful, like this is a heart. It was originally obviously pumping blood. Now, when the creature died, if it was in the right conditions, the blood with all its transition metals will invade this, and all of these different types of tissue, see the whiteness looking in a very darker thing, and this color and that color, all those are going to have different properties and molecules that want to stabilize with a specific exact transition molecule attachment. Now, here's what this heart did or would do if it was in this condition. You see the colors? Those are all transition metals. Now, this is basically an opal. Now, I had somebody come and I posted about opals, and he said, that's not an opal. I forget what he said it was, but I don't think he understands that all of this has a whole batch of different types of stone in it. There could be crystals, and there could be opals, and there could be just layers of basically tissue that, I don't know what you call it, but it wouldn't have that opal look to it. But anyway, this gets confusing, so I'm going to do the whole new video about opals, because I really did a terrible job. And he was right. I should have, talked about this. You see this? This is what opals are made of, like these little balls. Crystals are a whole different story. This is what the crystals are here. And he mentioned that all they do is they name them by these different angles, different types of stone. Well, opal is just, I think it could very well be blood cells, because they take these right out of the dead center of the hearts, the best ones. Or they could be muscle too. But that's from, I believe they chiseled this right out of the center of a heart because of all of these transition metals. And again, I showed these over here, right in the center of this heart. Where is it? You see them right here? All those are the same transition metals. And those were in the blood and they just solidify. Now, on the outside, you have different types of opal-ish things and metalloids and all that stuff. But right in the center, is blood, and blood has blood cells, and blood cells have membranes, and membranes seem to isolate whatever is in that contents, and then they structure themselves in organized patterns and in structures. They're not really crystals, but they almost look like crystals. Look, this is what crystals look like. They're all organized and they lay in like this pack and so forth. They attach in these different angles. Well, a circle is a circle. You can't attach it in an angle, but you can attach it like this. And you see them running down all these. They look like just like they're in crystalline, but they're not because they're circles. It's the only difference. And then they radiate though, like flash off of this surface against that surface and rounded instead of angle, like, you know, like the crystals. Crystals are, you know, they flash, but they don't do the same thing like opals. So the guy was right. He was right. But I want to show this in extreme detail so that we don't have any more confusion, because really all it is a clash of words. My main focus is to understand what transitioned into what under what circumstances. Now I understand the colored invasion, and I think this is muscle. You see this right here? You see these blocks? You see that little tiny stripe right down the center of these blocks? You see these squares? All right, and then you see all these little dots here. What the hell's going on there? I believe these are sarcomeres, which is a muscle, and they pull in like this across these to pinch together through this little tiny layer. Now let me show you what they look like anatomically. Otherwise, I can't see any other reason for this. Now, what happens in these little pockets is a seed crystal gets in there, and then it just grows that same color until it hits the membrane. All right, so let's see what they look like. And here they are right here. That's what a sarcomere is. Remember those little blocks and those little stripes? And then inside here, there's all those little tiny, you know, blood cells, basically, as far as I'm concerned. And when they harden up, they look like this, the same blocks. And that little stripe down the center, and the stripes over here. You see a stripe? I see no other possibility here. So anyway, I'm going to leave it at that for today. I sent off to Secretary Miguel Cardona, who is the Secretary of Education. I sent this off to both of my senators, Blumenthal and Chris Murphy. And I said, Yale University is standing in front of education, plus they plagiarized my work, and they took funding from NASA, and just basically told them what I told Yale. Now, I don't know what that includes, but I'm going to tell you what, it's a disgrace. And plagiarism is fraud. And Peter Salvoy, the president of Yale, seems to think that's fine. He won't respond to anything that I've sent over the course of almost 10 years now. It was 2015. 2015 I finally wrote my paper, had all my research done, everything done. They knew all about it. And then they wrote their paper in 2016, took a bunch of money, I don't know how much, but from NASA. I paid NASA. You pay NASA. You think that's right? I don't think so. There's a lot of this going on, and we need to straighten out these kind of abuses in the system. And they're just taking advantage of kids at Yale. It's a very terrible disgrace when you consider that an Ivy League school. I consider it a poison Ivy League school now. All right, I love you all. Thank you.